And last time we discussed the basics of conduction. So in continuation, today we will be discussing the steady state conduction, and we will obtain the equation of that in Cartesian as well as cylindrical and spherical coordinates, and then we will apply this equation or these equations to various types of geometries of the bodies having different geometries, the plane surfaces as well as the curved like the cylinder and the sphere, etc. So generally you get at least one question in subjective type exam from this part, and in objective type exam you will get questions from this part. So before starting, let me remind you that you can ask any question by writing in the comment box, and if you like it, then please share and subscribe the channel. So let us begin with the Cartesian coordinate system. So these are our x, y, z axis. This is x, y and z, and let us take a cuboid, the element in the shape of cuboid, such that the heat is entering into this element in every direction and leaving at the other face. This is the origin, and the faces are so this is the x direction, and heat is entering, suppose at a rate of qx, and it is leaving the other side, that we have to find. Similarly, heat is entering at the rate of qy in the y direction. So let me show it here. The heat entering this face in x direction is qx, and it is leaving this face. And similarly, in y direction it is entering at a rate of qy and leaving along this face, and it is entering at a rate of qz and leaving along this face. So we have to find what is the heat entering into the system and what is the heat leaving at the other face. Suppose thermal conductivity of the substance is K, and we can assume this to be constant, although the thermal conductivity is varying with respect to temperature. That we will be discussing later on. How does it vary? So here, for the starting purpose, I am taking this to be variable, but later on we will assume this to be a constant. So mass of the element is m, density is rho, and the specific heat is C. So I can write that by using the Fourier's law, heat entering through the face in x direction. You can write the expression for that, and before this let us take the sides of this along x-axis. The side is this OA dx, along y-axis this side is dy, and along z-axis this side is dz. So qx is minus of Ka. What is A? The heat flowing perpendicular to the direction, that area you have to take. So qx is flowing perpendicular to EDCO. So this is a rectangle, the area is dy into dz. So dy into dz, dy into dz multiplied by the thermal gradient. Thermal gradient means change in temperature. Suppose dt is the change in temperature over the length, that is dx. So this is to be written as a partial derivative, because the temperature is varying in 3 dimensions, x, y and z, and this is the heat flowing per unit time. So if I take time d tau, so in this time this much heat is flowing. So this is the expression for heat energy which is entering the phase, this phase along the x-axis. Now what is the heat that is leaving? Qx plus dx, heat leaving through the other phase. So this is Qx plus dx, and similarly this is Qy. So the heat leaving is Qy plus dy, Qz and Qz plus dz. So this I can write by using Taylor's approximation, Qx plus del over del x, Qx into dx. So minus k into dy dz del t by del x d tau plus minus k dy dz del t by del x d tau into dx. So this is the expression for heat entering through one phase, and second one is the expression for heat energy leaving the other phase. So now we can write the difference of these two, that will give us the net flow in the direction of x by taking the difference, or heat which is remaining inside this, heat retained by this, or you can write net heat flow in x direction. So difference of these two, this will give us del over del x of k dy dz del t by del x d tau into dx. So this minus this is equal to the net heat flowing in the x direction, heat coming in minus heat going out. You can also write that this is the heat which is retained by the body, net heat, or I can write this as heat accumulated in the body in x direction equal to this. So here you can see that all the terms inside the bracket, they are being differentiated partially with respect to x. So except k and this term, you can treat all of them to be constant. So del by del x of k del t by del x into dx dy dz into d tau. So what is this quantity? Dx dy dz is the volume of the element, dv, volume of this element multiplied by the time. So if I take k as variable, then I will have to write this inside this, then I have to take the derivative of this. If I take k as constant, then this can be taken out. So k can be varying in x direction also, in y and z direction, or k can be varying at the same rate in the three directions, or k can be taken as constant. Here we will take this as constant. Similarly, you can write the expression for heat accumulated in y and z directions. So I can write the net heat accumulated equal to, this is the sum, this is the heat accumulated for heat flowing in x direction, similarly write for y and z, and then sum. So this is equal to del by del x k del t by del x plus del by del y k del t by del y plus del by del z k del t by del z, and the remaining term, this will be common, dv into d tau. So this is the expression for net heat retained. Now what happens because of this? The heat which is accumulated, the temperature of the body will increase. Suppose the heat generated, the body is also generating the heat. Heat generated inside the body is equal to Q dot. Heat is generated at this rate inside the body. So we can write that according to first law of thermodynamics, Q is equal to delta U plus W. So here W is 0. There is no thermodynamic work. So we can write Q is equal to delta U. So what this heat is doing? Heat is flowing through this. So that there is a difference of heat entering and heat flowing outside. So heat is retained inside the body as a result, and heat is also being produced inside the body. So as a result of this, the temperature of the body increases, which causes an increase in internal energy of the body. We have discussed what is internal energy. It is the sum of potential energy, kinetic energy, magnetic energy, vibration energy, etc., etc. of the molecules or particles of the system. So temperature is a factor which is a energy increases. So we will apply the first law of thermodynamics here. So net heat accumulated. So I will write that del by del x, k del t by del x plus del by del y, k del t by del y plus del by del z, k del t by del z, plus the heat produced inside. And let me explain this. Where is the heat produced? Like in case of the heat is produced inside the body, and in several other chemical processes also the heat is produced. So that's why we are taking this. If heat is not produced, then this term will be 0. So how much is the heat produced? Q dot per unit of volume per unit of time, and this is also to be multiplied by volume and time. This must be equal to, what is delta U? The change in internal energy is equal to mass into specific heat into delta T per unit of time. So these two must be equal. So this is equal to mass is density into volume, rho into dV into specific heat, mc del T by del tau, rate of change of temperature with respect to time multiplied by the time, d tau. There is a difference between these symbols. This is exact differential, this is partial differential, because t here is a function of x, y, z and time. So we can differentiate t partially only. So this is the rate of change of t with time, and these are the rate of change of t with space or x, y, z directions, and we have multiplied this by dt, that is a finite quantity. So this gives us the change in t. So on both sides these terms will be cancelled. Now if I take k as a constant, suppose k is constant, not a variable, then this can be taken outside the differential, but t here is a variable. So I can write del square t over del x square plus del square t over del y square plus del square t over del z square plus q dot divided by k. I am dividing the both sides by k, taking this outside, equal to, now here we have this term rho into c, and when divided by k we will write this as rho c by k. So this is written as 1 by alpha, 1 by alpha, and it is del t divided by del tau, that is the rate of change of t with respect to time. So friends, this is the expression for heat flow in Cartesian coordinates with a system which is having constant value of thermal conductivity, and the heat is generated inside this. Now first of all, this is a three-dimensional heat flow case, means heat is flowing at the same time along x, y and z direction in Cartesian system. This is a case with heat generation. This is a case with constant thermal conductivity, and this is unsteady if this term is not zero. Why? What is unsteady? Unsteady heat transfer means that del T by del of time is not equal to 0. If it is steady state heat transfer, in that case temperature remains constant with respect to time. It does not change at any point. So this is called steady state if the temperature is constant with respect to time at any point. Otherwise, if it is varying, then it is called unsteady state heat transfer. So this is the general equation which gives the variation of T with respect to space and time. Now what is this term alpha? Alpha is, you can see here, alpha is equal to K by rho C. So this is defined as thermal diffusivity. This is the ratio of two terms. K stands for thermal conductivity, and rho C, rho into C, this represents the sluggishness or the thermal inertia of the body, the capacity of retaining the heat of the body, retaining or the heat flowing through it, how fast heat can flow through this, or for how long the heat can be retained. So how fast heat can flow through this depends upon the term K, the thermal conductivity. So if a body is having large value of thermal conductivity, that is the metals like solid metals, K is large, and obviously you know that the metals they have very small value of thermal inertia, sluggishness. So rho into C is small for those bodies because they heat at a very fast rate and also they cool at a very fast rate. So alpha will be high for these. And if for a body like we have water body, pond, etc., or any other fluid, molten metal, etc., the value of K is very small, thermal conductivity is very small, and rho into C, the thermal inertia, sluggishness is very high because they can retain the heat for quite a long time. So that's why water heats very slowly, but it longer period. So in that case alpha will be small. This term is high, this term is low. So alpha will be small, thermal diffusivity for non-metals which can retain the heat, which do not easily conduct the heat, and for metals etc., or good conductors for which K is high and sluggishness or thermal inertia is small, the value of alpha is high. So friends, this is the equation. Now this, according to Fourier's equation, can be written in this form also: grad square T. Grad square is the operator, del square by del x square plus del square by del y square del square by del z square, plus the heat generated Q dot by K is 1 by alpha del T by del tau. This is our equation of heat flow for a system having three-dimensional heat flow, and heat is generated inside the system, the body, and it is unsteady state of heat transfer. Now our further discussion will be based upon this.